All right, everybody, welcome back. Today we're going to do is we are going to work on sketching the graph of polynomial functions. So we are going to start with something we're a little more familiar with, and we're going to start taking a look at a quadratic function first. The first thing we want to do is we want to go ahead and try to factor. So in order to do this, we are already in quadratic form, so we can use our diamond math or our box method to go ahead and factor. So if I use our diamond math method, I should have two factors, and now I'm looking for two numbers that multiply to a negative 36 and then add to 5. Well, those numbers are going to be a negative 9 and a positive 4. So when we go to factor, because this is a quadratic, I know that the beginning term in each binomial is going to be x and x. Now, using the diamond math method, we are going to have a negative 9 and a positive 4. So this is the factored form of the original quadratic. This is what we've been doing previously, but now what we want to do is we want to actually solve. So these are the factors, x minus 9 and x plus 4, but in order to solve and find the solutions, we need to set each one of our factors equal to 0 and solve. So we do that using order of operations. I'm going to add some values over. We get x equals 9. And I'm going to subtract 4 over here, and we get x equals negative 4. Well, now what I can do is I can sketch the graph of this polynomial. And I'll do a little bit better job of creating a grid for us. If we look at the graph, we can see that we have x-intercepts now at negative 4 and then positive 9. All we know is that our quadratic function is going to pass through our quadratic at that point. But let's not forget we also know about our end behavior. Our end behavior focuses on this leading term. In order to focus on the end behavior, we know we need to focus on our degree and our leading coefficient. The degree is 2, which is an even number. What that means is the end behavior should be the same, either both up or both down. Now, that leading coefficient is a positive 1, so it tells us our end behavior should be both, again, because of the degree, going up. So we know that we want to go through these points and back up here. What that means is our quadratic is going to be shaped something like this, and this is a sketch of our polynomial function. Now, eventually we'll add some more details there. Like I know we do know how to find our vertex down here. I do know that we know how to find our y-intercept, but this is just a rough sketch, and this is what we're going to start with. So what happens is if we have a polynomial, we can get each of the factors. Well, if we have each of our factors, we can solve those to get each of our roots or our solutions, which then give us our x-intercepts. These are important because it tells us where our quadratic function is going to pass through the x-axis, and therefore we have a rough sketch of what this polynomial should look like. Now, we can do this with other polynomials as well. So in this case, I have 4 terms. So I'm going to use the grouping method, and I'll switch colors here for us. I'm going to group the first 2 terms together and then the last 2 terms together. Now, focusing on this first grouping here, I want to divide out what they have in common. This should actually be a cube. If I divide out what they have in common, I should have an x squared. And then if I'm dividing by x squared for each of those terms, I am left with an x and a plus 5 on the inside. Now do the same thing for our other grouping. We have a negative 9x and a negative 45. Well, I'm going to divide out their greatest common factor, which is negative 9. And when I do that, I am left with negative 9x divided by negative 9 is just x, and negative 45 divided by negative 9 is a positive 5. So I know I'm about to get the right answer, at least in terms of factoring, because the inside of these parentheses are the same. So if I focus on these being individual terms, I can divide out what they have in common. And then what I have left is my other factor. So this is the factored form, but we can actually go further. Remember, when factoring, we always want to try to break up our factors further if possible. So this first one is going to stay the same. We still have an x plus 5. There's only two terms, so if factoring that, we'd want to look for the sum and difference of cubes, which neither of these are cubes, or the sum and difference, or the difference of squares. Now this next one, x squared minus 9, those are both perfect squares, so I can use my difference formula. That's a squared minus b squared equals a plus b times a minus b. So what that means is I can split this up into two parts, and I have x and x in both, and then a positive 3 and a negative 3. So this is the factored form of my polynomial. As we talked about last time, once I have the factors, I can then find my solutions by setting each one equal to 0 and solving. So these are my solutions of the polynomial. Once I have my solutions, I technically can then find my x-intercepts. Which means I can start to graph. So if I go ahead and create a quick coordinate plane here, I can plot my x-intercepts at -5, 0, -3, 0, and positive 3, 0. So I know where my function is going to cross through the x-axis. Well, the next thing I want to do is think about that end behavior. And to focus on end behavior, again, we look at the degree and the leading coefficient. Well, my degree here is 3, which is an odd number. An odd number degree tells me my end behavior is going to be opposite. That means I'm going to go down on one end and up on the other. That is all determined by the leading coefficient, which is 1 and positive. So how I try to tell my students to help remember is we go down to the left, up to the right. It's kind of like that disco dance move, down to the left, up to the right. Because this leading coefficient is positive, that means there is no change. So we should go down to the left and up to the right. Now, I'm just going to connect these points with a smooth curve. I pass through the first x-intercept, then go down and pass through the next, and then I'm going to curve back and pass through my last x-intercept. So this is a brief sketch of what that polynomial function is going to look like on the graph. Now, again, we could get more specific, and eventually we will. We could figure out what that extrema value is going to be, this extrema value. We can find out what our y-intercept is going to be. But again, right now it's just a rough sketch, so we don't really need to worry about that just yet. All we're doing is we are factoring to find solutions. Once we have solutions, we can then find our x-intercepts, which tells us where our polynomial crosses through the x-axis, and we use our end behavior to give us a rough sketch. All right, the last problem we're going to do is over here. And again, we've got another grouping problem. You know what, why don't we change that? Let's do something a little bit different. Let's do x to the 4th. Let's see if I can do this in my head. Minus plus x minus 20. Is that what our other one is? No. All right. So I've got this polynomial. It's a little bit different because I have higher exponents. But because it's in quadratic form, then we can treat it like a quadratic. So I'm going to set up in two different factors here. Now, because these first two terms are going to need to multiply to x squared, I'm going to have an x squared and an x squared because the middle term is x squared. If we had multiple terms, it might be something different, but it's not going to be because of that middle term. Now, I need two numbers that are going to multiply to a positive, multiply to a negative 20, and add to a positive 1. That's going to be a negative 4 and a positive 5. So I've got positive 5 and a negative 4. Now, I can set each one of those equal to 0, and I can solve. Well, realistically, I should factor this a little bit more. So the first one doesn't factor anymore because it is not the difference of squares. It's a sum of one square and one non-square. So we can't do anything with it. But the x squared minus 4 is a difference of squares. So that means it can be factored again. I'll start with x and x because this is an x squared. And now I need two numbers that are going to multiply to that -4 but add to 0, which is a 2 and a -2. So now I'm going to set each one of my factors equal to 0. And I can solve. Well, the problem over here is I end up having to take the square root of a negative, which is okay, but we end up with a negative number. So if I take the square root, I get x equals. Well, every time there's a square root, I need a plus and a minus. Whenever we take the square root of a negative, I need an I. And then 5 doesn't simplify, so it's going to stay like that. We'll come back to this one. Subtract 2 and 2 over here, I get x equals -2. And then add 2 over here, and I get x equals 2. So I have +2, -2, and then plus or minus I root 5. Well, I can't have imaginary x-intercepts. So what that means is we aren't going to talk about this one just yet. So in our graph, I only have 2 real x-intercepts. So if I sketch out this coordinate plane, I've got -2, and then I've got +2. And my degree here is 4. So end behavior means I need to focus on the degree and the leading coefficient. Well, my degree is 4, which is even, so that means my end behavior should be in the same direction, either both up or both down. What determines that is the leading coefficient, which is a 1, and it is positive. So that means both of them are going to go up. So I'm going to go up through here and up through here. Now, I don't know what the middle looks like. It could look something like this. It could just look like a quadratic and look like this. So really it doesn't matter. The key part is getting our x-intercepts narrowed down and then having the end behavior, okay? So I actually want to do one more here, and the one I'm going to do is, I'll keep it simple, and we'll do a quadratic again. I'll keep it nice and simple. So this we can factor. If I go ahead and factor, we get x plus 2 and x plus 2. Well, really what I did is I did our diamond math, 2 numbers that multiply to +4 and add to 4, it's 2 and 2. So I end up with my factored form, which I can then find my solutions to by setting them equal to 0. So I actually have 2 of the same solutions. So it causes something interesting to happen. I only touch my x-axis at one point. Well, if I go to sketch the graph, I should only touch at -2, 0. Well, how is that possible? We know a quadratic either looks like this or it looks like this. Well, if I were just to, let's just focus on this one for now. If I were to take this and put it over here, we have 2 x-intercepts. If I put it further down, still 2, still 2, still 2, still 2. The only way I have 1 is if we only touch at one point, which would actually have to be the vertex, the lowest point. And coincidentally, that's what this function is going to look like. We're going to go up in both directions because my degree is 2, which means even. And then my leading coefficient is 1, which is positive. So I should go up in both directions, but we don't cross through that x-axis anymore, and so this is what our solution is going to look like. And again, it's not super accurate because we're not considering y-intercepts and things like that, but right now we're just setting the baseline. We're building the foundation so we can more accurately graph these polynomial functions a little bit later on. So something interesting happens here that I want to talk about. Because we have 2 solutions that are the same, that technically means we've got 2 factors are the same. When we have multiple factors that are the same, we need to focus on how many of each factors are. So here's what I mean by that. There is something called a multiplicity. A multiplicity is really the number of times a factor shows up in the factored form of a polynomial. So in this case, we see x plus 2 twice. That means the multiplicity is 2. Now, all of our other examples, each of our solutions only show up one time. That means the multiplicity is 1. Same idea over here, 1 and 1, and then 1, 1, and 1. Well, look at all those examples. When our multiplicity is 1, we just pass right through them. We pass through each of these x-intercepts. However, when our multiplicity was 2, once we went down from that function, we intersected at that x-intercept, and we went right back up in the other direction. We call that a bounce. So when your multiplicity is even, that means that the function is going to bounce at that x-intercept. And this is what this is right here. Normally an x-intercept is where we cross through the x-axis. But if the multiplicity, the number of times we see a factor is even, in this case it is 2, then we are going to bounce and go right back into that same direction. If it is odd, then that tells us we are going to pass through. So let me give you a scenario. If we were to have a 4 there, well, technically now we have 5 of these. 5 is an odd number, so that means that when we get to that intercept, we would pass right through. Now, if I did change that to a 4 up in the exponent, we have 4 and then 1 here. Technically, my degree is 5, and my end behavior would look different. The key idea is, no matter what the multiplicity is, if it's even, we pass through. If it's even, we bounce. If it's odd, we pass through. So maybe it's a better idea to look at something like, let's do this one. If I were to regraph this real quick, we still have the same x-intercepts, but let's just say, ignoring this for now, I had a 2 there and a 3 there. So it changes the whole polynomial, but the idea is this root, when we look back at the factor has a multiplicity of 2. That means when I hit at 9, my intercept, I need to bounce back and go in the same direction. Now, this multiplicity is 3, which is odd, which means I pass through. So my end behavior now is going to be different. And it's different because technically my degree is 2 plus 3, which would be 5. And my leading coefficient, let's just say, is still positive. So my end behavior needs to be different. I'm going to go down in one direction, down to the left, and up to the right. Now, because I only have these two x-intercepts, something interesting needs to happen. The even multiplicity is going to bounce. So instead of passing through at this x-intercept, I'm going to bounce and go right back up before passing through this x-intercept because the multiplicity is odd. And sometimes odd multiplicity is greater than 1. It might look like a little curve through, but nonetheless we pass through. So the ideas for the day. We can factor polynomials. All right, and when we factor, we can find solutions, which leads us to x-intercepts, which helps us graph. We plot the x-intercepts and use our end behavior to kind of connect the points. Now, multiplicity is the number of times that factors are seen in the factored form. If that multiplicity is even, we bounce and we don't pass through, just like this one right here. And if it is odd, we pass right through that x-intercept. Okay? If you have any questions or concerns, please feel free to leave a comment. Thanks for joining.